Hey, welcome back to Abstract Algebra. In this second video lecture from chapter 4, we're going to focus on the ring of integers mod n. So you can see our goals there. The first goal is really the primary goal of it is to show that this abelian group, Z sub n, finite abelian group, is actually a ring under addition and multiplication mod n. All right. Then we're going to specialize off to the case where n is a prime, and I'm going to try to show you that ZP in that case is actually a field. So it's an interesting example because it's a finite object and it forms a field. And then towards the end, we're going to use our group theory to make little work of proving a couple of famous theorems that typically come up in a number theory class. But we'll see from an algebraic point of view that they're really just kind of simple consequences about some group theory that we already know. Okay, so they're called Fermat's little theorem and Euler's theorem. So that's the outline. Let's see if we can't make it through it. So I've kind of started us off here. Let's fix an n. And we already know that the addition of equivalence classes in Z sub n, addition of cosets that's defined by that operation is well defined. Yeah. So here A and B, didn't quantify it. But A and B, I won't pronounce the brackets, but I mean them. They are, of course, any two elements of Z sub n. And that's coset addition or addition mod n. We know it's well defined. So I have a lemma here that says that the similar operation where you multiply the class containing A and the class containing B by taking the class containing their product, I claim that's well defined. Yeah, and you guys know what that means. So let's just get into the proof. Suppose you had two elements, say A and alpha, and they represent the same class. B and beta, they represent the same class. I have to show you that the class containing AB is the same as the class containing alpha beta. Okay, so we've done this a lot. So I skipped some of the details here in writing it, but if A and alpha represent the same class, then that means that A is equal to alpha plus some multiple of n. Yeah, so that's the what it means to be congruent mod n. Likewise, B is beta plus some multiple of n. What are the multiples? I don't know. There's some integers, k and j. All right, so then we just look at AB, replacing A and B with what they equal in terms of alpha and beta. And then I did a little algebra here. You can check it. You can pause the video and check it. But all but one of those terms has a factor of n in it. So I factored it out. And that precisely shows that the class containing AB is the class containing alpha beta because AB minus alpha beta is a multiple of n. All right. So the operation of coset multiplication mod n is well defined. And now the fact that Z sub n is a commutative ring with unity 1, it all follows from those properties in Z. I'm actually going to leave it to you to prove that. Maybe I can make some pieces of it homework problems. But what do I mean by that? I mean, like here, I started writing out the distributive law. So one of the things you'd have to check is, does the product of A with the sum of B and C distribute? Well, what do you mean by the sum of B and C? You mean that thing, and then we just proved that this multiplication is well defined. So once I'm inside the brackets there, I'm looking at that, which A times B plus C, which is AB plus AC, because the integers do have the distributive law. And then blah, 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 blah. Same thing for the commutativity, the fact that 1 is the identity. I'm not saying that it can be skipped. You should do it as a student learning this stuff, but absolutely everything will go through. The fact that this is well defined is what the whole issue was. And then everything else is going to follow because those properties follow in the integers. Okay. What did I do down here? I just made, I picked an n, Z3. It's got three classes, 0, 1, and 2. And I just made the addition and multiplication tables. I won't really say much about them here other than now we have two operations. And so you can add and multiply those classes. Notice over here in the multiplication table that like 0 times anything is 0. Makes sense. Notice that 1 times something it returns, it's the identity. And then, well, the kind of peculiar entry, I guess, is 2 times 2. 2 times 2 is 1 mod 3. 2 times 2 is 1 because 4 is congruent to 1. So it's kind of interesting. 2 is its own multiplicative inverse, mod 3. Yeah, okay. So here's what I want to prove. Another lemma. If you take a prime number and you choose an element of ZP that's not 0, Okay, so you take some element that's not divisible by p, then you can find some other class in ZP that's also not 0, and you can multiply them together and get the identity. So another way to say that is that if A is not 0 in ZP, then A is a unit. Yeah, it's our new vocabulary. Unit means invertible. A has a multiplicative inverse. So here's how I'm going to try to convince you of that. Take your A that's not 0, okay? If it's not 0 in ZP, it means it's an integer that's not divisible by P. If you're not 0 in ZP, you're not a multiple of P. And because P is a prime, that means that the greatest common divisor of A and P actually has to equal 1. Yeah, because P is a prime, it only has 2 divisors, 1 and P. And if P doesn't divide A, then the GCD of A and P has to be 1. So an old result of ours from this class, the greatest common divisor of 2 integers is always an integer linear combination of them. So I can find integers x and y so that ax plus py is equal to 1. And if I reduce that equation mod p, if I look at their equivalence classes, well, p, of course, is 0 mod p. So the left-hand side of that thing just becomes ax, which by our well-definedness is a times x. So we can just take b to be the class containing x, and it's also not 0 because p doesn't divide 1, right? If b was equal to 0 mod p, then this expression would show me that p divides both terms on the left-hand side, so it would divide 1. Cool. So every non-zero element of ZP is a unit. We put that together with the fact that ZP is already known to be a commutative ring with unity, then we've proved kind of a main theorem of this lecture, that if P is a prime number, ZP is a field. ZP is a finite field. It's a field with P elements. If we look at the non-zero elements of ZP, I'm denoting it by ZP star a little guiltily. I probably, because this whole class we've been denoting non-zero elements by a prime, but it doesn't look right to me. So ZP star, I've defined it there. It's the classes in ZP that aren't 0. They form a group. They form a group because why? Every non-zero element of ZP is a unit, so every non-zero element has an inverse. The multiplication operation is associative, and so on and so on. So it forms a group of order p minus 1. ZP star, oops, sorry, has p minus 1 elements in it because not every element, well, because we're throwing out 0. Sorry, my tongue is dripping all over the place in this video. Cool. So we can prove a famous number theory theorem from that. It's called Fermat's little theorem. I've written it here in kind of number theory language. It says if you take a prime number and you take an integer that isn't divisible by your prime, then the p minus first power of that integer is congruent to 1 mod p. So let me give you kind of an algebraic or group theoretic proof of that. So first of all, if p doesn't divide a, then that means that a is not 0 in ZP. So that means that a is an element of this group, ZP star. And you guys remember that if you take an element of a group and you raise it to the order of that group, you have to get the identity in that group. Yeah, that was from an old result that when we were looking at Lagrange's theorem. So this precisely means that the p minus first power of a is 1, and that is just the abstract algebra way of writing that a to the p minus 1 is congruent to 1 mod p. So really, from an abstract algebra group theory point of view, Fermat's little theorem is just a fact about finite groups, that ZP star is a group of order p minus 1. So yeah, you raise an order in a group you raise an element of a group to the order of that group, you're going to get the identity. Cool. Okay, I wanted to look just one more topic in this video, trying to keep it short, but I wanted to relax the condition and look at Zn for any n. Because our work above would still show us something. If you take an element of Zn whose greatest common divisor with with n is equal to 1, then that element will still be a unit, because it's still true, if the greatest common divisor of a and n is 1, then a and n still have some linear combination that equals 1. And so the same argument would show that a times x in Zn is 1. So that argument that we gave above in ZP is valid. If your GCD with n is equal to 1, then you're a unit. You're a unit in Zn, all right? And conversely, if your GCD is bigger than 1, then you're not a unit. In fact, I claim you have to be a zero divisor. Let me try to convince you of that. If the GCD D is bigger than 1, well, then n over D is less than n. It's also bigger than 1. Yeah, D can't equal n because A is an element of Zn, and D is the GCD of A and n. So A is less than n, so D can't be n. So this thing, n over D, is also a non-zero element of Zn, right? But if we multiply A with n over D, I can rewrite that like this. D divides A as well. A over D is also an integer. Yeah, and so I'm just multiplying A over D by 0. That's going to give me 0. But A and n over D weren't 0, so those things are zero divisors. Cool. So I know I'm talking fast. You'll have to pause this video and kind of write down and think. You can ask me in class, but I'm just talking fast so the videos don't get too long. But what we just showed is that in Zn, that an element is either a unit or a zero divisor. And how do you tell? When the GCD of A and n is 1, it's a unit. When the GCD of A and n is bigger than 1, it's a zero divisor. Cool. Well, you guys might remember earlier in this course, we defined this Euler's phi function. It doesn't have anything to do with a homomorphism. Phi of n, it's the size, counting the absolute value of how many numbers between 1 and n are relatively prime to n. Remember that function? It's called phi of n. And what we just proved above is that the ring Z of n has phi of n units, right? Because there are phi of n values of k that are relatively prime to n. Each one of those values would be a unit if and only if. Phi of n units. Notice that if p is prime, how many numbers between 1 and p are relatively prime to p? All but one of them, yeah? So ZP has p minus 1 units. We already proved that above in this lecture. Oops, not his, it's has. ZP has p minus 1 units. I don't know why I'm dotting my A. Cool. All right, so last result. If you're a number theory student, you've seen this before. If not, it's your first time maybe. But if you take two positive integers, A and n, and A doesn't actually have to be positive, but that's okay. You take two positive integers and they're relatively prime. Then if you raise A to the phi of n, you'll always get one congruent mod n. So what's our proof of that? Well, the group of units in Zn has order phi of n. That's what this claim. Z of n has phi of n units. If the GCD of A and n is 1, then A is a unit. And if you, by Lagrange, take an element in a group and you raise it to the order of that group, you have to get, the identity in that group. So that means that A raised to the phi of n's equivalence class is the same as the equivalence class of 1. And that's just the abstract algebra way of writing that A to the phi of n. So here, I guess I'm kind of speaking to number theory veterans, but these two theorems, Euler's theorem and Fermat's theorem from number theory, from a group theoretic point of view, they're the same theorem. They both say that if you raise an element to the order of a finite group, you'll get the identity in that group. It's just that in the Euler's theorem case, that finite group is the group of units in Zn. Yeah, so it has order phi of n. Fermat's theorem is actually just a corollary of it, because phi of p is p minus 1. I'll end this video just by saying that actually Euler's theorem implies Fermat's theorem, because phi of p minus, or phi of a prime is p minus 1. So Euler's theorem is often called a generalization of Fermat's theorem. Okay, I hope that you were able to concentrate through that. I'll hope you see me in class and you can ask me questions about all this stuff.